this video, it says we have a fountain with an opening of radius 0.15 meters, shoots a stream of water vertically from the ground at 6 meters per second. It says the density of water is 1,000 kilograms per meters cubed. A wants us to find the volume rate of flow of water, and then B says that if there is a pipe beneath the ground that has a radius of 0.25, it wants us to calculate the absolute pressure at that point, 2.5 meters below ground. And then part C wants us to find what the owner of this particular fountain would have to do in order to shoot the water 4 meters up into the air, okay, by adjusting the radius of this nozzle. All right, so if you need to pause, read that again, and then get a good sense of what's going on in this problem. So to do this, to do part A, to find volume rate flow, I know I need to identify a couple of things. Here it says already the radius of the the radius of the pipe that's above ground is 0.15, and then it also gives us a speed. So I'm just going to go ahead and identify this arc in the diagram really quick. I'm just going to call this part of the pipe that's above ground R2 because I want to go from bottom up. So I'm going to reference the pipe later on as 0.1 because I'm just going to go from bottom up, okay? It's up to you. You can go from bottom up and call the bottom 0.1, and this is 0.2. I'm just going to go from 1 to 2 vertically. All right. So here's R2, the part of the pipe that's above the ground is 0.01 meter. And then from there, you know the speed here is 6 meters per second. So to do flow rate, I can just use A times speed, A for area. And here in my function, I put A2 V2 because I'm referencing, again, the area above the ground to be reference point number 2. Okay, so to do that, I'm just going to go ahead and identify A2 V2. V2 is given here in the diagram, which I just drew out for you, which is 6 meters per second. So we can do plug and chug now. A is just pi r square, and then V here is given as 6. So therefore, R2 is given as 0.15 meters. If we square that to find the area of the cross section times the speed when it leaves this particular junction above the ground. So that will give us a flow rate of 0.0424 meters cubed per second, and that is your answer. Okay, that's it for part A. That's pretty easy. Part B. Part B says that the fountain is fed by a pipe at one point has a radius of 0.25 meters, and it is located 2.5 meters above the fountain's opening. Well, to help you visualize, here is the part of the pipe that is beneath. And you notice I drew this part of the pipe wider because the radius here is larger. It says the radius of this part of the pipe is 0.025 meters, which is larger than 0.015. All right, so I'm just going to call the radius of the pipe as R1. As I said earlier, I'm just going to go from bottom up, so from ground to above ground. And then the radius of this opening earlier already is R2, which is given. Okay, so to do this, we can just set up Bernoulli's function because I'm calling the bottom as reference 1, above ground as reference 2. P1 is what I'm trying to find because it's asking us to find the absolute pressure at the pipe at 2.5 meters below ground. So in order to do so, I like to go ahead and define my reference point. Here, 2.5 beneath the ground, that's going to be my 0 point because I'm going to go from bottom up. So here, I'm just going to call H1 as 0, and then I can measure from there upward. So that distance there is 2.5 meters up, okay? So it wants us to find the pressure at 2.5 meters beneath the ground inside that pipe. All right, because I identify H1 as 0, I can go ahead and cross out this particular term in Bernoulli's function. Well, rho g H1, H1 being 0, so anything times 0 is just 0. So I need to go ahead and solve for P1 because P1 is my pressure underneath the ground, okay? So it all depends on which well, it all depends on how you define your 1s and 2. Again, you can go 2 and 1 or 1 and 2 like I did. So I'm going to find P1. To find P1, I need to get rid of 1/2 rho V1 square by moving it to the left side. Well, excuse me, by moving it to the right side. So on the left side here is positive, so therefore when I move it to the right side, the sign changes, so it becomes minus 1/2 rho V1 square. But as you can see here, you have similar terms. You have a 1/2 rho V2 square. You also have a 1/2 rho V1 square. You don't have to move things. You can keep it the way it is I have on the screen, but I'm just going to go ahead and combine or move things so that similar terms are in the same proximity. Okay, so here The only thing difference is that I just moved this negative 1/2 rho v1 square so that it's next to the other 1/2 rho v2 square. Okay, why? Because now I can factor out the 1/2 and the rho. You don't have to factor it out. Like I said earlier, you can keep it as is, but I'm just gonna go ahead and factor it out on my work because I like to factor things out. All right, but excuse my dog if she's barking. She apparently is being ferocious this evening. All right, so P1 equals P2 plus, once again, both these terms right here in the middle that I'm going back and forth with my cursor has a 1/2 rho in common. So I'm just going to factor that out. And I want to keep v2 squared minus v1 squared in parentheses. And then the last term hasn't changed, so I just carry that down. So I'm just going to plug in value. P2 is atmospheric pressure, because when the water leaves this particular part of the pipe, it goes into the atmosphere, and the atmospheric pressure at that junction is 1 atm, but 1 atm is 101,325 Pascal. Okay, so this is a constant. So this is 1 atm. I just needed to convert it to a Pascal because Pascal has units of kilogram, meters, and second square. All right. I'm not doing anything fancy here. All I'm doing is substituting in. So the 1/2 gets carried down. The density of water here is substituted in for 1,000 because it's given. V2 is 6. Don't forget to square that. V1, I don't know what V1 is. I don't know what the speed underneath the pipe is. And then the last term, rho, is 1,000 again because given. G is 9.8. And then the height here is 2.5 because it's 2.5 meters above the ground. So as you can see, in order to find P1, we need to find what the speed inside the pipe is, right? How fast is this water flowing inside this vertical pipe that's 2.5 meters below the ground? So to find V1, I can just go ahead and set up continuity equation. Here I need to find what V1 is, so therefore I need to divide both sides by A1. So V1 is A2 times V2 divided by A1. I'm just going to substitute A2 and A1. The definition of area, once again, is pi r square. And because it's A2, I substitute out for R2. And the area on the bottom is A1, so therefore it's pi r1 square. Well, you know R2, you know R1, and you know V2, right? And pi is going to cancel out because there's a pi on top and bottom. So if you use the same reference point that I did, R2 is the radius above the ground, which is 0.015 meters. Point R1 is in the diagram here is the radius of the pipe beneath the ground, which is 0.025 meters. So if you do that properly in your calculator, you should get a value of 2.16 meters per second. So that is how fast the water is flowing inside this wider pipe. Okay. All right. Other than that, I'm just gonna go ahead and substitute in for V1 in the P1 statement because that was the only thing holding me back. So if you do things correctly, the first term gets carried down. 1/2 times 1,000 is 500. I just simplify a little bit here. 6 square is 36, and then 2.16 square is 4.67. And then if you clean all this up on the last term here, 1,000 times 9.8 times 2.5, you get 24,500. And this is in units of kilogram per meters times second square, which is the same as Pascal. Okay, so Pascal is all this junk condensed. So instead of saying kilogram per meters times second square, it is now just known as Pascal. So everything is in the same unit. So therefore, we can just clean this up. Everything in the middle here, the 500 times 36 minus 4.67, that will give you 15,665. And everything is now in the same unit. So therefore, we can just add all this up in a calculator. If you do that correctly, you get 141,490 Pascal. And that is our answer for part B. Okay, so the pressure in the pipe that is 2.5 meters beneath the ground is that many Pascal. All right, part C wants us to find the radius that the nozzle has to be adjusted in order to shoot the water 4 meters into the air, right? So to do that, we don't know what what this radius is. Watch my cursor, right? Before, it told us that the radius of the pipe above ground is 0.015 meters. But this new scenario says, well, it wants to shoot the water 4 meters above the ground. So we need to adjust the nozzle. Well, do we make it wider or narrower? So we have to figure that out. So I'm just going to call this VI. I don't know how fast the water is coming out now, right? Because we're adjusting the nozzle. So before it was 6 meters per second. Now I don't know what it is. But what I do know is whatever the speed is, it has to make it all the way up to 4 meters high. Because that's ultimately what the owner wants to do. How fast does this water have to shoot up so that it reaches 4 meters and fall back down? Well, to do that, you go ahead and set up the flow rate function again, because for this one, for part C, it's important to, hopefully you read it. It says that the owner wants to deal with the same flow rate, right? Well, this is the trigger that you should set up Q equals AV because it sets the same flow rate. We already found Q earlier, okay? We found Q earlier as 0.00424 meters cubed per second. Well, I don't know what this new area is because we're adjusting this nozzle, so we're adjusting the radius. So therefore, instead of A, I'm just gonna call it pi r squared. But I don't know what r is, right? Ultimately, we're asked to find what this new radius is gonna be, so that it shoots this water up, so that it goes up 4 meters high. V, I don't know what that V is. Okay, so do not plug in 6 meters per second here, right? I don't know what this new velocity is. Why? Because I don't know how high it goes previously. All right, so therefore, to solve for r here, I'm just gonna clean this up a little bit. I need to get r squared by itself first, so I need to divide both sides by pi and v. So in my work, the only thing difference here is I kept the numerator on the left side, and then the denominator has the pi and v because you divide both sides by pi and v. But then you notice this is still r squared. So to get r by itself, you would just radical both sides. So I highlighted v because v is the only thing that's kind of keeping us back here. Well, how do we find v? Well, use kinematics, right? This is where kinematics and fluid kind of play nice together. Well, I'm just going to use common form. I can use VF minus VI squared equals 2G delta Y. I'm using this because I know VF is 0. It says here it wants to launch the water 4 meters high, so at some point it has to come to a stop and fall back down. So VF here is 0. So because I know VF is 0 when objects change direction, really this function simplifies down to just negative VI squared equals 2G delta Y. Well, G here in kinematics is negative 9.8 because it's slowing the water down. And then what's delta Y? It's delta Y is going upwards, so that's going to be 4 meters, which is given in the statement in part C. So if you clean this up, the negative signs cancels out because there's a negative sign on the left, negative sign on the right, that cancels out. So VI squared is going to be 78.4, and then we need to square root that to get VI by itself. So if you square root 78.4, you get 8.85 meters per second. So how fast does this water have to shoot out? It has to shoot out at a rate of 8.85 meters per second. So now that I solved for VI, I can go ahead and substitute in. Okay, so I was missing V, I just found V. So V is going to be 8.85, and if you do all this on your calculator and square root it correctly, you'll get that the new radius is 0.0123, which is actually narrower than what it started with, right? It started at 0.015, now is 0.0123 meters, which makes sense because you're trying to get it to go higher. Therefore, you have to make it more narrow. All right, and other than that, that is the answer for this particular part, and that is it for this video. All right, I hope that helps. Stay nerdy, don't be whack.